Hi, welcome to this lesson on trigonometry, trigonometric functions part 1. Let's have a look at question 4. In the diagram, the graphs of f of x equals sine x minus 1 and g of x equals cos 2x are drawn in the given interval, negative 90 degrees to 360 degrees inclusive. The graphs of f and g intersect at the point A, which is labeled here on the graph. And B, 360 degrees negative 1, is a point that is given on the graph of f. So that's been given to us, so we can put it there. Okay, so that's the information we've been given. They want us to first of all write down the range of f. Okay, so f is this function here, sine x minus 1. And remember, range, the parameter that affects your range is the b value. So the general form will be a sine bx plus p plus q. So the b value here affects the period, and because the b here is 1, that means that your period, or the range rather, we're looking for the range, not the period of f. The range of f, right, that's going to be influenced by the y parameters that get affected. So from that same generalization, the things that affect your values for your range is going to be your a value and your q value. So this parameter here and this parameter here. Okay, as a reminder, your A is your vertical stretch or compression depending on the A value, and your Q is a vertical shift up and down of the entire graph depending on the value. So here A is 1 in front of the sine x and Q is negative 1. So that brings the entire graph down. So recall that the standard parent graph sine x, the range is from negative 1 to positive 1 inclusive. So if the entire y values need to move down by negative 1, so they're going down 1 unit, then the new range, so the range of f is, so if I go 1 down from negative 1, that's negative 2. And if I go 1 down from 1, that is 0. And if you look at the graph of f, you can see that the minimum value here is at negative 2. And the max value is here at 0. Okay, so at 90 degrees, yeah, y is your function f is 0. And the minimum points here, we can see at negative 90 degrees on the graph, you get negative 2. So that's the range, the set of all the y values on the graph. Okay, it goes between negative 2 and 0. Next, we want to write down the values of x in that given interval for which the graph f is decreasing. Okay, so let's come back here. So when does the graph decrease? That means as you read the x values from left to right, so from negative 90 degrees and you move all the way to 360 degrees, is the graph going up or is it going down? If it's going up, then it's increasing. If it's going down, then it's decreasing. So you can see the graph continues to increase, keeps going up as we go along the x-axis, all the way up until it reaches 90 degrees, which is a turning point. Then it starts to decrease, the y values keep going down until it reaches another turning point, which we can see on the graph is 270 degrees and negative 2. After that x point, the graph continues to increase again. Okay, so the interval where it decreases is going to be from here, from 90 degrees to 270 degrees. So that is the interval on which that graph is decreasing. So I'll say open brackets because we start at that value. We're not going to include that value because the graph can't be decreasing at a point. It's increasing within an decreasing within an interval. So it's from 90 degrees to 270 degrees. Now we're given that P and Q are points on G and F respectively. So that means P is an element on the graph of G and Q is an element on the graph of F. And the line PQ we are given is parallel to the y-axis. If PQ lies between A and B, determine the values of x for which PQ will be a maximum. So let's see what this question is actually asking us. So it says that here's A, the point of intersection, and here's B. All right. Now we know that P and Q are 2 points. P lies on G, so P could be any point here on G that I've marked here with a little x on the green graph, and Q is any point on F here, marking with a cross as well on the blue graph. And you can see I'm putting the x's in such a way that if I had to construct the line PQ anywhere between A and B, we get this line that is parallel to the y-axis. Okay, so it's a straight vertical line, and these are all the possible lines that can be. There's infinitely many of them. But we want to find the P and Q coordinates. Let's check. We want to determine the x values of the P and Q coordinates such that the distance between these two lines is a maximum. Okay, so let's try and break down what does that mean. Well, first of all, we need the equation of the line PQ to determine what it is, and therefore from there be able to determine what its maximum value is going to be. Okay, so let's get an equation for the line PQ. So P, because it lies on the graph of F, if I call its coordinates x1, y1, and Q, if I call it x2, y2, now we know that because P lies on G, that means that it must be satisfy the equation of G. That means if you substitute G of x1, you must get a y value of cos of 2 times x1. And because Q is on F, that means F at x2, that gives you sine of x2 minus 1. That's the y value associated with the x value for Q. Okay, looking at the graph, can we see that the P values always lie above the Q values? So if I wanted the distance of that line, I would take the y value of this P coordinate and subtract it from the y coordinate of the Q value. So therefore, that will give me the distance of that line PQ. So I can say mathematically the distance of line PQ, which I'll denote by that symbol, distance or magnitude of PQ, is essentially going to be the function g of x minus the function f of x. Okay, that's the y coordinates of the g function minus the y coordinates of the f function because g lies above f. So we'll guarantee a positive distance. Okay, but g of x is cos 2x and f of x is sine of x minus 1. And that must be the function here. Okay, so how do we determine the maximum of this? Well, right now, if I simplify this, it becomes cos 2x minus sine x plus 1. Right now, it's quite difficult to see what the maximum of this particular function is going to be. But if we can maybe manipulate this function into something more recognizable, then maybe we can try use that new function to be able to see with a maximum. Okay, so cos 2x being a double angle identity, I'm going to think maybe I can use one of the 3 variations of the double angle formulae. And because I already have a sine x term here, I think I'm going to invoke 1 minus 2 sine squared x as my simplification for cos 2x. Okay, so simplifying, I have 1 plus 1, that's 2. Okay, minus sine x minus 2 sine squared x. Okay, so how am I going to still find the maximum of this thing now? Well, now I can notice something. There's a squared term here and a sine x normal term here. So I'm going to be a bit smart about this. Whenever I see a square, I think of a parabola, a quadratic function, right? Okay, where there's a happy face, there's a minimum, and when there's a sad face, it's a maximum turning point. So because this looks like a quadratic, what I'm going to do is I'm going to invoke k substitution. I'm going to say let k equal sine x. Then the distance of the line PQ can be written as negative 2k squared minus k plus 2. Now that's something more recognizable, right? That is the equation of a quadratic, and because of the negative 2, your a value being negative 2, which is less than 0, that means we have a sad face, which guarantees that there's a maximum of this thing here. So what is the maximum of a parabola? Well, there's a nice shortcut for it, right? For the x coordinate here, x was given as negative b over 2a. That's a very important result from parabolas in terms of where to find their x coordinate for the turning point. So if I use that here, so my a value is negative 2, my b value is negative 1, and my c value is 2, then I can say this line here will reach a maximum when the k value is equal to negative b over 2a. So that's a negative 1 over 2 times negative 2. Negative 1 is positive 1, 2 times negative 2 is negative 4. So at negative a quarter, when k is negative a quarter, this straight line here will achieve its maximum distance. So let's substitute that back. So therefore, PQ is equal to negative 2 times negative 1/4 squared minus negative 1/4 plus 2. Okay, so let's simplify. Negative 1/4 squared is positive 16, or 1 over 16. And then times negative 2, that's negative 1 over 8. Then you're going to have negative negative 1/4 is positive 1/4 plus 2. So negative 1/8 plus 1/4. 1/4 can be written as 2/8. So 2/8 minus 1/8 is just 1/8 plus 2. So that's 2 and 1/8, or 17 over 8. So that is going to be the maximum distance, okay, 2 and 1/8, or 17 over 8. But that just gives us the distance. We want the values of x for when that'll be a maximum. So how do we do that? Okay, so let's make some space here. Okay, so let's just write down what we've got so far, right? So far, we worked out that the maximum distance of PQ was going to be 17 over 8. But we want the x-coordinates of P and Q that'll give us that maximum distance. Well, as we were doing with that formula, we arrived at something like this. We said that K equals negative 1/4 would give you the max of that distance. But we also had K equals sine x when we did the substitution. So these two are K, so sine x must equal negative 1/4. So from here, we can solve for x now. All right, so this is a trigonometric equation. Let's get our cast diagram up. Where's the sine negative? In the third and fourth quadrants. Okay, so the reference angle is going to be sine inverse of positive 1/4. And if we do that, we get 14.48 degrees. Okay, so that's the reference angle. So in the third quadrant, x must equal 180 degrees plus that reference angle. So add 180. I get 194.48. Okay, and then the period of sine is 360 degrees. And then in the fourth quadrant, we must have x equals 360 degrees minus this reference angle. So I'm going to push 360 minus answer, and I get 345.52. Okay, plus k times 360 degrees, where k is an integer. So now, remember, we're in this given interval here, negative 90 to 360. So we need to just find the x values for which is satisfied in that given domain. Okay, so for quadrant 2, if I put k equals 0, then I get an x value of 194.48 degrees, which is in that interval, so it's fine. K greater than or equals to 1, that's going to be much bigger than 360 degrees, so that's not applicable. And k less than or equals to negative 1, that's going to be, well, let's check. All right. So we have 194.48 minus 360. That gives us negative 165. That's outside the given domain, so not applicable. Okay, so we'll just keep getting more negative. Okay, and then for the quadrant 4 solution, if I put k equals 0, I get x equals 345.52 degrees, which is in the interval, so that's fine. K greater than or equal to 1, no applicable solutions, right? You're going to get values much bigger than 360, and then k less than or equals to negative 1. Let's check what that's going to be. So let's bring it up here. So we have 345.52 minus 360. That gives you negative 14.48. All right, and that is in the interval. Okay, so if I put a negative 2 and onwards, we're going to get values that are way out of negative 90. So let's go ahead and check which of these three, okay, are valid. So we have these three here. Okay, so if I go back here now, it says it must lie between A and B. So now we didn't work out the value of A, but we can see that A is greater than 90 degrees. All right, and we can see B is 360 degrees. So essentially your solution now gets restricted further between something that is greater than 90 degrees. Okay, so I'm going to put something open brackets and 360 degrees. Okay, so PQ here, the x values we found, 194. That makes sense. That looks like it's somewhere over here. Okay, so that makes sense. What about 345? Yeah, that makes sense as well. That's like somewhere over here. And then the last one we found was negative 14. But that's all the way out here somewhere. So because we wanted it between A and B, we discard that solution. Okay, and that is how we would do this type of question. I'll see you in the next one.